Okay, so I'm not going to go over the syllabus and stuff. I'm assuming you guys know how to read, which is good. But first, I want to say congratulations on getting into this class. I'm sure some of you might be on the wait list. This class was supposed to be scheduled for 130 people. We only got 90 in here. So unfortunately, there's going to be a lot of people who don't graduate potentially on time, which is really sad. But from what I've heard, if you know any folks in the situation, I believe the department is trying to teach this course in the summertime to make up for the shortfall. So hopefully that's nobody's position here, and everybody gets into the class. But as you can see, we are at capacity. We cannot add people because it is a fire code violation. Okay, so I do want to go over a couple things that I think are pretty important. Most of y'all I don't know. A couple of y'all I do. Hopefully, if I do know you, it's because you took simulation with me. But that said, I want to go over a couple things on how this class is going to operate, because it will be, I'm always making adjustments semester to semester. So the first adjustment is, and I think we did this last time in stochastics, for the most part, we don't deal with any administrative issues in the classroom, right? So if you have a question specifically about the course, go ahead and just ask it here. Usually I'm pretty good about answering. Give me about 48 hours. I don't answer emails on weekends, okay? So don't expect that to happen. So if you message me on Friday at 5 o'clock, you're probably not going to hear back from me until Monday. I might, depending on what it is, but no expectation there. So if you have a question about the class, go ahead and put it there. If you ever have a question about material, post your question. These are all discussion posts. Post your question in here. I encourage you all to answer each other's question. I'll try to answer them. Valeria will hopefully look at them as well. Is Valeria here? I don't think she is. She has class right now. She's our TA. She's TA'd the class before. She's pretty great. So please refrain from administrative questions. When I'm done with this, I know some of you are going to be tempted to raise your hand. Don't. Okay? Well, maybe, but I'll probably cut it off. Especially if it has anything to do with the syllabus. Okay. One thing I do want to say, and I do this to my Pearl and your Pearl, I don't know why. I'm sympathetic to y'all because I was a student at one time, and it really sucks when you're sick or if something happens. To miss one lecture is kind of a big deal. So I do post these lectures on YouTube, okay? I'll make a comment about that. Again, this is a service. Don't expect me to do it. I don't have to do it. I don't even like doing it. It takes me about an hour of time each time. It's really distracting, okay? But I do it for y'all because I know life gets in the way, okay? And so, yeah, so I'll put some videos up. Sometimes we'll put additional videos, like if you guys ask a question in one of the units, like, hey, I've gone over the book, I've read this YouTube stuff, or I've seen the lecture, I came to lecture, and then I watched the YouTube video again, I just don't get some concept. Can you give an example problem? We'll probably post some videos in the supplemental video section, but we'll also integrate them into the modules with direct links. So that sort of leads me to this guy, which is how to do well in my classes. Well has different meanings for everybody, but I think it's more or less the same no matter what. Number one, come to class. That really shouldn't be a shock. You guys pay thousands of dollars to be here. I don't understand why. I suspect only 30 to 40% of you will actually show up, which really sucks for everybody else who's on the wait list, but that's your decision. Come to class, complete all your assignments, actually turn in good work, okay? I think you'll find, if I have any sort of reputation, hopefully that reputation is if you turn in crap work, I'm gonna punish you horribly, right? So if you think you turned in 60% work, which is good enough, you're probably gonna get 30% or 20%, okay? That's just unfortunately how I grade. I'm pretty linear until a certain point, in which point I'm gonna hammer you. So turn in good work. Don't be lazy. Actually pay attention. Okay? Get off your cell phone. So I'm going to tell you that I can see everybody in this row. I can see about 4 rows or 5 rows back there. 4 or 5 here. And then maybe the first 3 there. Okay? If I see any of y'all on your cell phone, I'm going to tell you to put away. If I see it multiple times, I'm just going to kick you out of class. It's super distracting to lecture when people are on their cell phone. It's like talking to your boyfriend or girlfriend about something serious and they're going like this. And you're like, okay, that's kind of not cool. Okay? So especially here and in front, don't use your cell phone. The lady right there with the laptop, I definitely can't see you if you're on your cell phone. Probably not. So that should give you some idea, but if I do see you, I'm going to ask you to put it away. Okay, yeah, so don't distract me. And I think for other students, sometimes that can be distracting. Okay, so like, if you want to do well in so first bunch, how do you pass, okay? Unfortunately, I will probably say this is the hardest class in IE, okay? Not because of me, but because of the material, okay? So, unfortunately, some students didn't pass the last time I taught it. I really don't want that to happen, right? And there are some students who actually did the first 3 bullet points and didn't pass. And so that was really disappointing. But again, this is a hard class. Don't expect this to be like all your other classes. Well, sorry, I don't want to say that. Don't expect this to be like some of your other classes in IE. I really do think this is the hardest one, and I think most of my colleagues would agree. Okay, so you want to get an A or something like that. How do you do it? Get off your cell phone, pay attention, sit in front. All right, I think most people, hey Adam, good to see you. I know a bunch of y'all. Okay, cool. Sit in front. You guys have the highest chance of getting an A, and then, I forget, it's basically anybody who's in direct line sight with me. You guys will probably get B's and C's in the back. Okay, that's sort of the reality. Like, your odds of getting a C goes up significantly the further back you sit and the less I can see you. Okay, so if you want to do well, really try to scoot forward. I know there's a full class, but at some point, folks won't start coming and shuffle on down or get here early. Come to office hours. I really like talking with y'all. I've had students come to every single office hours to just work through problems. I have no problem doing that with y'all. I actually love teaching. I just hate grading, okay? If you really want to understand the material, whenever I teach it, you should ask yourself how and why. Why is that true? How did that happen? Okay? But when I say ask yourself how and why, that does not mean, Professor, why is that true? That means you actually look at it yourself. Okay? How to fail, skip class, right? Which unfortunately some of you will do. Cheat is a really good way. Turn in lazy work. Okay. Now, I do want to put this up because I think this was probably something that, unfortunately, some folks didn't know when I first taught this class, and maybe they weren't exposed because this class is a little bit different. Okay, so how do you actually study for my exams? Understand engineering exams are all about solving problems. So, if you want to do well on an exam, you practice solving problems, right? It's not that radical of a notion, but I know that when I was a student, and I know a lot of y'all, you think studying is reading a book or rewatching these YouTube videos that are going to be on lecture, or lecture videos that are going to be posted on YouTube. I'm going to tell you this. If you're watching my videos to study an exam, then you're already behind, okay? Our goal is to make sure nobody is behind, and so please come to lecture, right? Really, reviewing the YouTube videos should only be if you're really confused on a topic. But if you're watching whole lectures to study, that's not a good idea. I think there's more effective use of time. So really, if you want to study for an exam, practice problems, practice problems, practice problems. We are engineers. We solve problems. Yes, sir.
sorry to interrupt on that, but with the required textbook and the access code, do we have an online thing that we need an access code to study problems or do homeworks or anything like that?
To be honest, I have no idea. I use the physical textbook.
Okay. So
Yeah.
Just you get the
Yeah.
physical textbook.
Yeah, get the physical textbook. I think that's the way to go. I don't even know. Is there an online version of this book?
Yeah.
Oh, there is?
But in like the UCF bookstore,
So
when
we're-
you look
yeah.
at the class, it says something with access.
Oh, all I care about is the physical textbook.
Cool.
Yeah. So, you'll be submitting. You'll write your homework on paper, and then scan it and upload it to WebCourses. So there's no like online stuff required. Okay. So, sort of following on this idea of how to do well, it is worth noting, what does a credit unit actually mean? And I know Keith Lee will sometimes talking about this. And this is actually a legal definition, which really surprised me. So basically, in this class, in all your 3-unit classes, you should be doing about 9 hours of work each week. If you're not doing 9 hours of work each week, you're probably behind. So just keep that in the back of your mind. So these are my general ideas on how to do well. Unfortunately, I know, again, this is a hard class. I get it. This class does leverage a lot of probability and statistics, and if that is one of your weaknesses, there are parts of this class that will be very painful. Okay? Period. Yeah. So, really, I want to encourage you guys, I'm going to go through some problem stat, but if you need help working through some of it or understanding it, I'll post a link to a YouTube channel that I think is one of the best. Probably it'll do a better job than I can, but I can certainly help out with some probability if you come into office hours, and we can work through some problems. Okay. Any questions on what I've said, but not the syllabus? Cool. All right. Awesome. Okay, so we're gonna. So, the good part is all my notes are written up now, so hopefully you can, if you want to download them in advance, or if you're sick or ill, you can sort of look at the notes. I'll try to update them as I can. So let's see. All right. I'm hoping me writing notes here in OneNote works for y'all. I actually really like working on whiteboards, but I don't see any sort of camera here to record things. So maybe we'll figure that out later if we have to, but if you have trouble, we'll sort of go from there. Okay, so the foundation, or let's start with this. We have 2 classes in operations research. One is deterministic. That means we know everything about the world, and so we can optimize and solve it and do whatever we want. The other is stochastic, okay? And what we mean by stochastic is essentially random, right? So there's going to be some sort of random process or random outcome or some sort of measurement that we're not quite sure of that's going to make it hard to make a decision, right? And that's really the foundation of this class, is going to be how do we make decisions when we're confronted with uncertainty or randomness. Okay? And so it's actually worth sort of defining what randomness is, especially for engineers, and where it's coming from and how it sort of shows up. Okay? So for the most part, I want you all to think about randomness as uncertainty of outcomes. And there's usually one reason or 2 reasons, and they're kind of closely related, about where randomness comes from. Okay? Randomness is not arbitrary. There actually isn't really such thing as randomness. Really what randomness is, and our uncertainty to measure and predict the world, is due to our inability to measure or model the world perfectly. Or we'll say exactly. Okay. That's it. Okay. So I don't have a coin with me, but I think I've discussed this with a bunch of y'all. At one point in my life, I learned how to flip a coin perfectly to get heads every time. Okay? Flipping a coin is not...
I want to see that.
I might be able to do it. Give it a shot. I doubt I could do it again. Okay, so I got tails. That's fine. Doesn't matter. Tails again.
So you could say it works 50% of the time.
Tails again.
Never mind.
We can't tell either way.
Tails again. Tails again. Okay. How did I do that? Why is me flipping a coin not random? I'm pretty certain if I did this over a whole semester, I could flip whatever I wanted 20, 30 times in a row. What am I doing?
Manipulating it? Your outside circumstance?
No.
Consistency of the play.
Consistency of the flip. Right? Who's the greatest free throw shooter? Who was it? Rayon? I think it was somebody else. It's some guy who made like 20,000 straight free throws. Right? I don't even know if he was a professional player or not. But anyway, so this guy, he's just consistent. He does the same thing every single time. He can control the motion of his arm. He understands the weight of the ball and how much force is required. Okay, if it's inflated, deflated, he sort of figures it out, right? Adjusts. Okay? There's no randomness in him shooting the ball. Okay? The randomness comes when you're unable to measure or model what's going on. Okay, that's really what randomness is. Okay? So the reason why flipping a coin is random is, one, most people don't even try to understand how hard they're hitting it, right? Or when they're catching the coin. Okay? So if you want to get good at flipping this coin thing, all you have to do is be consistent, right? Flip it the same amount, catch it at the same place. You can also sort of time it a little bit, depending on the rate of rotation. Sort of 3 little tricks, and then you can flip the same thing over and over and over again. Okay? So it's all about control, right? Or measurement, I guess, really. So randomness is the lack of those things. And a lot of times in the world, we're sort of presented with this problem where we don't have information, right? We can't measure it, maybe, or maybe our measurements are bad. Okay? And that's really what randomness is all about. Okay? And so typically, when we discuss probability, we're talking about random events or outcomes. Okay? And these are all within the context of an experiment. Okay. Now, these events or outcomes come from something we call a sample space. And usually when we're talking, so a sample space is a set or a collection. And so usually if you ever see me talking about a set or collection, I'll use something sort of scripty. So, and it's always going to be uppercase. So here we have an uppercase S that's sort of scripty. Right? And this sample space tells us all the possible events or outcomes that can occur. All right? So when I flip a coin, typically there's only two outcomes that can occur, heads or tails. I have seen it land on the side once, which is really weird. But that's our sample space, heads and tails. Okay? Now, these sample spaces can be discrete or continuous. All right, so what do I mean by that? Well, we'll start with a discrete sample space. All right, so rolling a die. Okay. So let's say we have one die that we're going to roll. All right. The outcomes, that sample space, is 1, 2, 3, 4, 5, 6. Let's say it's a 6-sided die. Okay. And so these are the possible outcomes that can occur. All right. Now, it is worth noting a couple things that make them unique or interesting. One, this is countable. All right. These are mathematical terms I'm using, so hopefully you'll learn some math. Again, sets are always capitalized. S's usually bold or scripted. I think the book uses that notation as well. These curly brackets define our set notation. Okay. And this set is countable because we can actually name each of the items. 1, 2, 3, 4, 5, 6. Okay. Not only is it countable, it's finite. Okay? Because we have a fixed number of them. So you might think, well, what does a countable infinite set look like? It certainly exists. So we could talk about, let's say, the number of ants in a colony. All right. It could be 0, 1, 2, 3, ... off to infinity. So the shorthand of writing this is Z. So there's the set of integers that are positive. Okay? Or sometimes this is called the natural numbers. So again, S is the name of our sample space, the set. Okay? That set is just equal to positive integers. So Z is the symbol for the set of positive or set of integers. Plus here tells you we only allow positive. But that's also the same thing as saying natural numbers. Okay? So some useful mathematical notation if you don't remember it. They all mean the same thing. Now, there's always a discussion, does the set of natural numbers include 0 or not? I don't know. It's not up to me, but I usually include 0. Okay, so the neat part about this set, I'll get you in a second, Garrett. It is countable, right? And it's countable because you can name every number. Yes, it might take you, well, even though it stretches off to infinity and it will take you, well, you'll never finish counting or naming the numbers in the set, you can still name them, okay? So even though it's an infinitely sized set, it is still countable. All right, so it's an infinite set that is countable. Yes, sir?
At what point does it have to, or is it classified as infinite? Because before this, if you would have asked me how many ants are in a colony, I could probably tell you it's a finite number of ants, but...
No, it's a countable. Well, why would it be finite?
At some point, you have to get to the last ant.
But they keep it produced.
Yeah, what if they keep having kids?
Yeah, but at the same time, I mean, that's why we have things.
But we don't know. So part of that is we don't know, right? Okay, I see your point. We're sort of splitting hairs here, but
Yeah.
like it's true, they might reproduce faster than you can count them, but
So in that case,
is that, I'm asking, is that the definition of infinite? Just,
infinite is
it spans.
there are
less
an
than-
infinite number, right? So whether this is a physical practicality or not does not matter. All right. So
Okay.
yes, sir.
So it's just because.
Brent,
there's a-
right?
Yes.
Yeah.
Just because there's like a blank curtain behind it, like the anthill, so you're not able to really tell how much it is, and that's why we consider it infinite. Like,
If you want, I can give a different number. I mean, is anything in this universe truly infinite? Besides, actually, no.
Universe itself.
Actually, universe has a boundary. Believe it or not.
Now we're getting into philosophy.
Yeah. So I mean, this is why it's. Yeah. Oh.
So we can say they're countable and finite. Are we ever going to have a situation where we have like qualitative sense for the numbers or no?
Yes. All right. So here we have numerical numbers. We can certainly talk about other sorts of sets that don't have numbers involved with them. So student names. You know, Bob, Jose, Jai, ... Oops. You know. We can make this finite or not, right? Let's end with William. And we can close it off if we wanted to, right? But I'm sure you could make the argument there are in fact an infinite number of names because we can toss together any number of letters that we'd like, right? So the number of words that could be created is certainly infinite, right? But countable. Okay, so student names. And so the thing here is our sets don't even have to be numeric. Okay. And if they are numeric, they don't even have to be ordered like, or, you know, regularly spaced like 0, 1, 2, 3, 4. So on a football play, how many points can I score? 6. What else? 3. What else? Yeah, so an extra point that counts as a play. Yeah.
Yeah.
So I was confused when I looked over my notes again. I go, how do you score 1 point? So again, this is the extra point. What is this, a safety? This is a field goal. Or, oh wait, safety touchback? Or what? What is it when you tackle the guy?
That's a safety.
Safety, okay, yeah, okay. Oh yeah, 2-point conversion, right? Okay, for the extra, instead of taking the extra point, you scored, yeah, okay. And then we have the touchdown, right? All right, so we can see, you know, even when we have sets of numbers, they don't even have to be regularly spaced, right? We have 1, 2, 3, 6, right? Completely skip 4 and 5. And so we have a lot of flexibility in how we define our sets. And these are, you'll notice these are all sort of correspond to events, right? So if I pick a random name in this classroom, let's say these were all your names, right? I will get, you know, maybe I'll get Jose or Grant or Adam. If I dig up an ant colony and I actually have the time to count them, I'm going to get a number between 0 and whatever. Who knows? Okay. So yeah. Okay. So these are all examples of discrete sample spaces. And again, they're all the way you want to think about it is these sample spaces are tied to some sort of experiment or some sort of measurement, right? So the first one, I'm rolling a dice. I want to see what pops up. Second one is maybe I'm a researcher who studies ant colonies in Brazil, right? And I want to understand how big are ant colonies in Brazil versus Alabama. Okay, and so I measure the distribution. Right? Or student names, right? These are all tied to some sort of experiment that we might run. Okay. So conversely, we also have continuous sample spaces. And in this case, the outcome does not come from a set that's countable, right? It's infinitely dense. Right? So we could talk about the time between hurricanes. Yeah, it's about right. Did we have a hurricane this year? Yeah. Kind of, sort of, not really, right? We missed school. Yeah. So if we talk about that sample space, so if we want to use set notation, right, we're going to say it's the set of T, okay, such that, so that's what this bar means, T is greater than 0, and T is an element of the real numbers. And again, all sets are going to use this funny script, right? I usually try to be careful about that. So there's real numbers. Okay. So again, this is time between hurricanes. It should make sense, hopefully. You can logic it out. The time between hurricanes has to be greater than 0, right? Because if it was 0, they'd literally be on top of each other, and that means technically they'd probably be the same hurricane. Okay. So another way that we could think about this is just all. Actually, I'll teach you a neat little way people write things. We could actually say this set is the set of positive reals. And I might get this wrong, but if you do the /0, that means without 0. Okay, so there's all positive real numbers. All right. Later on, we're going to deal with Markov chains, and we can talk about the movement of a particle. So at each time we look at where a particle moved. Do you guys have to take 3 semesters of physics? No. Any of you took the 3rd one? You didn't. So you guys never learned about Brownian motion and stuff like that. Okay. So neat little experiment. Actually, Einstein got his PhD for Brownian motion. Basically, what it was sort of like a water droplet. And if you look at a piece of pollen in it, right, so he looked at it under a microscope, the pollen would sort of bounce around inside of the water droplet on the surface. Okay? And the reason why it was bouncing around is all molecules vibrate, right? And what would happen is the water molecules would sort of hit the pollen randomly in different directions. And so you get this motion of a piece of pollen inside of water. Okay. And so, if we were to talk about the position of this piece of pollen, let's say every 1 second, we might say, well, it's sort of random, or it looks random. The change in x position and the change in y position, such that delta x and delta y are both real numbers. Okay. So again, we're using set notation. The way you want to think about it is these are the elements inside of the set, everything to the right of this bar tells you the rules about how those elements are defined or what constraints exist on those elements. All right, so here, actually, we could maybe even add a constraint here. Let's say the water droplet had a finite radius of 1. Okay. Well, actually, we're not going to get into that. That might be a little more confusing. Okay. Yeah. All right. It is worth noting, and we do this in simulation, I think we talked about generating random numbers. So in simulation, we say one of the foundations of simulation is generating a random number between 0 and 1. Because in fact, if you can generate a random number between 0 and 1, you can generate a random number coming from almost any distribution, so this is very important. And so that sample space, the random number generator in our computer, will generate, let's say, a U, such that U is between 0 and 1. And maybe you include 0, maybe you don't. A lot of times you'll see it written like this. Or maybe like that. Sort of just depends. I don't think you can actually get 0 or 1 on a random number generator. And the requirement is that U is a real number. So U is a real number between 0 and 1, exclusively, excluding 0 and 1. Is the set countable? No. All right. So we should say not countable. In fact, almost, I think, yeah, all continuous sets are not countable. Is it finite? No. This is a good question. I'm not even sure. Actually, that's why I asked the question. I have to remember. This might actually be finite, but it's not. I can give it a different word. It is also, we'll call it bounded. Well, it certainly is bounded, right? If we go up to this hurricane one, this would be unbounded. So some of this is probably a little bit more than you need to know, but at least understand the set notation. You'll probably run into it a bit with me in this class. And it will sort of help when we start talking about probability. Okay. So when we are talking about the sample spaces, okay, each of the elements inside the sample space, so 1, 2, 3, 6, these are outcomes. Okay. Now, the reason why we talk about events sort of separately from outcomes is because events can actually be quite a bit more complicated. Right? So, E is an event. And this will correspond to a single outcome, or we'll call it an outcome, or combination of outcomes. Okay, and we'll sort of go through what I mean by that. And so usually what we talk about in probability is we talk about the probability of an event occurring. Okay. When you do your exams and when you do your homework, I don't necessarily expect perfect mathematical notation, but I expect you to mimic sort of how I write things in lecture. Okay, so please pay attention about how I write them. Okay, so I will give some leeway in how you write them as well, as long as it more or less follows what I do. So I'm basically providing a lower bound on how you should write your mathematical statements. Okay. So let's sort of talk about what are some events that we could calculate the probability. So let's say we have a student, and we might say, what's the probability of the student getting 1A in, so letter grade A, in one of their 4 classes. Okay. Well, depends on the student, right? Depends on the class. If all of my classes were writing humanities classes, this would be a 0. Okay. I don't think I ever got an A in a writing class. Okay. So why am I writing this and making a big point out of it? This is technically an event. Okay. So the real way you should probably write it is you define some event. We might call it event A. And you're going to say student getting 1A in 4 classes. All right. And then you'd say, what's the probability of E of A? Okay. So you'd do some calculation and fill that out. Okay. Now, if you're to do this first one up here, at least to me, I can understand what you're writing and what you're saying. So it's acceptable to me. But if you want to be mathematically correct, you define E of A, and then you say you're calculating the probability of E of A, right? Just be clear, okay? If you write something like PA, and you just put 1/4, I'm going to go, what the hell is PA? It means nothing to me, okay? You're going to get a 0. Tell me what you're doing. Work me through it. Pretend like I have no idea what you're talking about. Okay. Now, I think this is at least easy to read and I understand what's going on, so try to work in that direction. If you do this, I love you. It's awesome, but just make it clear about what we're talking about. All right. So in this first example, how many different types of grades can a student get? Actually, a bit more. We'll say 5. We'll just say 5. So A, B, C, D, F, Z, W, WM. There's a whole bunch. But let's an I, S. Yeah. So let's just pretend there's 10 different grades you could. Or let's just deal with A, B, C, D, D. We don't give Fs. Okay. Actually, Fs are well. We don't need to go into it. Fs are reserved for really, really bad. Because I think, doesn't it affect your financial aid if you get an F? I think it does. Yeah, no. No, but trust me, not passing your class never feels good. I've been in that position, believe it or not. So, it doesn't matter whether it's a D or an F. Okay? Either way. Okay, so, let's think about the sample space that we have, right? So let's say we're talking A, B, C, D, okay? That's for the options for a grade you can get in one class. how many classes are we talking about? 4. Okay, so how many different ways can you get grades in 4 different classes? 16, right? So, all right. Is that a finite set? Yeah. Is it countable?
Yes.
Yep. Is it discrete?
Yeah.
Okay. So usually when we're working with discrete sets and countable sets, calculating these probabilities are going to be pretty easy because you can go through all the different combinations one by one. All right. Things get a little bit weird when we start talking about continuous distributions. We have to be a little bit more careful. All right. A lot of times you'll see me write CONT, that's continuous. All right. And DIST stands for distributions. We have to be a little bit careful, okay? Okay. So at my notes, when I was writing them, my sister-in-law was pregnant, and we were very excited about my niece who was going to be born. So some of these might not make sense, but at the time they did. So one of the big questions you might say is, well, what's the probability of my niece? Okay, she was already born, but let's pretend she wasn't. What's the probability my niece is born at 8 a.m. exactly? And when I say exactly, I mean exactly. Okay. So, anybody want to take a guess? 0. Okay, that is. So, if I ever ask you, actually, this is a very useful skill for those of you who are taking the GREs, or just in life, if you do math, you'll learn that if anybody ever asks a tricky question, you basically only have a few options: 0, 1, sometimes -1, and what's the other option? Infinity. Okay? So these should be your go-to if you don't know the answer in this class ever, and I call you out. Just pick one of those 3, you'll probably be pretty close. Okay? In this class, you'll almost never have -1. But so this is also a good trick for GREs. A lot of times it's hard to solve system of equations, but you can plug in 0, 1, -1, and whatever, infinity into the problem and sometimes work backwards. So that's a very useful trick for those of you who are going to do that. Okay, so why is this 0? Well, it's 0 because with continuous numbers, right, number sets, you can't ever be exactly one thing, okay? Probability does not have density, enough density at a single point, okay? And so this is always going to be true, okay, when we're talking about continuous spaces. So another good example of this, let's see. Adam, how tall are you?
5, 6.
Are you, and what was the key word he said right before, 5, 6? About?
5, 6.
Yeah, well, you said about 5, 6, right?
Okay.
I don't know your exact height, and I certainly can't measure it, okay? So you're probably, I don't know, 5.513783669, you know, bunch of numbers coming after it. Okay. Let's say I could measure his height down to the nanometer. Would I expect it to be the same day to day? Let's say we took off his shoes and his socks, right? Would I expect it to be the same day to day? Why not? Yeah. So our spinal column certainly lengthens and adjusts from day to day, right? So I'm never going to get the exact same height every single time, okay? And the reality is the probability of me saying, hey, you're exactly this height, it's always going to be 0, okay? If you ever get interested in this, this is related to a field called measure theory. It's a lot of fun. Okay. So You can't ever measure anything exactly when it comes from a continuous distribution. It's not possible, okay? And so for that reason, we always assign it a probability of 0. All right. But that said, we should still be able to calculate probabilities of continuous variables. And the way that we do that is instead we group our sample spaces into chunks, okay? So again, let's sort of read this because I sort of calc with the dot probability over continuous sample spaces. So I know it's going to be a little bit annoying, but we'll get over it. So we group outcomes into chunks. So instead of asking, what's the probability of my niece being born at 8 a.m. exactly? You would say, well, what's the probability of my niece being born between 8 a.m. and 9 a.m.? Okay. That's actually something that has a non-zero probability. So this is how we're typically going to do things. Another example of this is we can't say what's the probability the bus comes in exactly 5 minutes, but we could certainly say, well, what's the probability the bus arrives within 5 minutes? Okay. All right. And so the key here is we're not talking about a specific instance from a continuous distribution or a continuous set. We're talking about a range. Okay. And so that's how we're going to calculate our probabilities when we're working with continuous distributions. Yes, sir.
Can you still define the range if you say like probability of my niece born before 9 a.m.?
Yeah, that would work as well. You probably want to put a bottom end on that, but I guess the implicit assumption is the day starts at midnight, I guess, right? Yeah, you could do that. As long as it sort of makes sense, I'm okay with it. All right, so I think this last example is good because it shows one way that we could maybe write out a probability statement in words. Okay, so if you were to write this, I'd accept it. Okay, or at least I'd find it acceptable. But we could actually be a little bit more specific about what's going on. Okay, so let's say T is the time the next bus arrives. Okay. Then the event E, we might define. So here we're saying this event is the bus arriving within 5 minutes. Okay. So the way we define that is we'd say, well, it's the set of T where T is between 0 and 5 minutes. Okay. And if you want to be, you could always put minutes there if you want to, as long as it's understood. Okay, so that's our event. In our sample space, is the set of T such that T is a positive real number. And we could do that if we wanted to, right? So T is in the set of reals that are positive, excluding 0. So this would be the sort of the more formal way of writing it out. But if you do it the first way, as long as I understand what's going on, that's okay. Yes, sir.
Is writing like t less than or equal to 5 the same thing as writing t is less than 5?
Yes and no. Okay, so mathematically, it is the same for continuous distributions. And let's sort of, it comes back from this idea. Okay? So we could think of the probability, and I'm going to just write it like this. The probability that t is less than or equal to 5, you could think of it as, well, that's the probability that t is less than 5 plus the probability that t is equal to 5. That sort of logically makes some sense? Okay. All right. But what's this value equal to? 0. So this is equal to 0, and so that sort of tells us that is true. Okay. There's actually a more mathematical way that you could sort of derive it, and we'll sort of get into this. So probabilities over continuous spaces, in fact, what you're doing is you're integrating. Now I'm going to do this. Oh, no. So we'll get there, but if you guys remember, if f of t is a PDF, in order to calculate a probability, we're taking an integral. Okay? The bounds of that integral, normally you'd write 0 to 5, but the correct statement is actually 0 to 5, or 0 to x, where x is taken to the limit. Okay, but we don't really do that because it seems a bit silly. And so we just really write 0 to 5 f of t dt. Okay. But again, we could retrace that as limit, and we should be careful, 5 from the negative side, 0 to 5 f of t dt plus the limit as, ooh. Oh, this is weird. Okay, if you don't want to write this down, don't write this down because it's very odd. Yeah. I would not suggest writing this down unless you really like math. Okay. So basically what I'm saying is the probability that t is less than or equal to 5 is the integral of the PDF from 0 to 5, or 0 to x, sorry, as I approach negative 5 from the left-hand side, plus the integral of f of t dt, but now I'm approaching 5 from the left and right side. So I'm going to squeeze it, all right? So again, this still leads to the same idea. This integral is equal to 0, right? Which corresponded to this guy. All right, so a little bit extra more math than you'd ever need to learn. But for those of you who like that sort of stuff, this is sort of fun. Okay. But we'll get to that probably in the next lecture or two. I think we have about 15 more minutes to go. Okay. So when we talk about the probability of an event, it's always going to be bounded, all right? All right, and so what we mean by that is the probability of E is always going to be between 0 and 1. So our probabilities can't be negative, and our probabilities can never be greater than 1. let's say I said our event, and this could be any event, but we'll say I'm rolling a dice, okay? And so I'm going to tell you, well, my event, I want to calculate the probability of some event, and I'm going to tell you, and the event is rolling a dice. The event is actually equal to the sample space. So what's my sample space for rolling a dice?
1, 6.
Yeah, 1, 2, 3, 4, 5, 6. So this is for a specific example, but this always holds true. All right. So if I say I want to calculate the probability of rolling a 1, 2, 3, 4, 5, 6, what should that probability be? Let's go back to what I just taught you guys. Wait, The answer is always 0, 1, or infinity. Okay? Can't be infinity because I just told you probability is between 0 and 1. So what if I roll a dice, what's the probability that I roll a 1, 2, 3, 4, 5, or 6? 1. Yeah. Okay. And so this is one of our first rules, which is in fact the probability of our sample space of everything is 1. Or let me rephrase that. The probability of an event occurring from within our sample space is 1. And actually, let me maybe be a little bit more accurate. It doesn't really matter. All right. So think of this sample space as everything. So an event is going to happen from the world of everything. What's the opposite of everything? Nothing. Okay, so the opposite of everything in math, we call it the null set. Okay, you might want to think of it as nothing. Okay. So what's the probability of nothing happening if I roll a dice? 0. Yeah, and again, tricky questions, especially in probability, are always 0 or 1. Okay. And so this is going to be actually a pretty useful concept down the road, these two guys. Okay. Because we're going to ask stuff like, what's the probability my pet is a dog and a reptile? What are the set of animals that are both dogs and reptiles? Nothing. No, right? So the probability of me having a dog and magical maybe, sure. The probability of me having a dog or a dog and a reptile is going to be 0. Okay. Of course, we'll have more pertinent examples down the road, but just setting the stage. Okay. All right. So a lot of times, we're going to be interested in combining events in interesting ways, and there's sort of the dog and reptile sort of thing. All right. And so we're going to start talking about, well, what's the probability of event 1 happening and event 2 happening? So, and statements are actually written a few different ways. This is the way that I learned to write it. The textbook would write it as E1, E2. So think of it like multiplication in a way. And in fact, they don't even refer to events as E1 and E2. I think the book, a lot of times, you'll see them write it as the probability of A times B, or probability AB. Okay? So these are all the same statement. Okay? These are all equal. Okay? But I think this makes sense to me. So I'm going to use this notation in class. But just be careful about the book. They write it a little bit differently. Okay? So actually, we kind of ran into this. Okay, so if events are mutually, how do you spell that? Mutually, yeah. So let's say we have some events that are mutually exclusive. That means they can't co-occur, okay? Sorry, then they cannot co-occur. Okay, so an example of this, we did dog and reptile, right? Okay, so let's say another one might be event 1, my niece is born in June. And event 2, my niece is born in July. Okay. Both those things cannot happen at the same time. It's either one or the other. Okay. And so visually, a lot of times, if we were to think of our sample space, so this is the sample space that corresponds to all the times my niece can be born. All right. So we're going to have 1 over here. This is going to refer to all the times in June. And we're going to have another one that's nearby, which is all the times in July. Okay, there's no overlap here. And so if we think about it in terms of Venn diagrams, oops. Okay. Because event 1 and event 2, if we think about them as sets, again, the sets of all times in June and the sets of all times in July. If we think about them and we say, well, E1 and E2, so what is the intersection of times and dates where E1 and E2 overlap? It's nothing, right? It's 0. Or it's this null set, okay? So we know that the probability of E1 and E2 happening, so my niece being born in July and June, is 0. Okay. All right, let's maybe do something a little bit more relevant. Still related to my niece, of course, or at least one that makes sense. Let's say E1, my niece is born in June. And E2, my niece is born on a Monday. So if we are still in 2019, and we talked about, well, E1 is a set, right? It's the set of all dates in June. And E2 are all the dates that are Monday. So if we talk about the intersection of E1 and E2, it's a set itself. And so let's pretend it is 2019. That includes June 3rd, 2019, June 10th, 2019, June 17th, 2019, and June 24th, 2019. Okay. Now, we could calculate the probability of E1 and E2, and actually this is a bit interesting. Do you think it's equally probable to be born on each one of these Junes? Monday. I think there's actually a slight skew. I don't know which way, but I'm sure there is one. Actually, on a related note, do you think it's more likely to be born on a Saturday or a Monday?
Monday.
Why Monday? Yeah. So doctors take off on weekends, right? So if you're a C-section, schedule you during the week, right? So you tend to have more weekday births than weekend births. I'm sure there's also other effects where people get stressed and stuff like that, but okay. So now let's pretend, where are we? Okay. Now in some cases, these events are independent of each other. Okay. So let's pretend the probability of being born on a Monday doesn't matter. All right, it's the same no matter what month you're in. Okay. And let's assume it's independent of the month. Okay. There's this really nice probability statement that when two events are independent, then the probability of event 1 and event 2 happening is just equal to the probability of event 1 times the probability of event 2. Okay, so what does this mean? So let's pretend probability of being born on a specific day of the week is independent of the month that you're born in. It's probably not true, but we can pretend. And let's pretend everything's uniformly distributed and whatnot. Then what we could say is, well, if they're independent, then we just need to know what the probability of being born in June is. And we can multiply that times the probability of being born on a Monday. And that would give us the probability of being born on a Monday in June. Okay? All right, so with that, with that, we'll wrap up and we'll continue more probability stuff on Thursday. Thank you, guys.